Today you have the last class from the first module. This is identical particles. The second part, we will be studying about helium atom. So now let us see first the Hamiltonian of the helium atom. Before that, let us just do the Hamiltonian of an atom having atomic number Z. Let it be the atomic number Z. It's not 2 now, it's now Z. So H is equal to sigma J1 to Z minus H cut square by 2m del J squared minus 1 by 4 pi epsilon 0 Z d square by Rj. What does it mean inside the bracket? The first part is the kinetic energy part. So if you have Z number of electrons, it will have J1 to Z. So J1 to Z number will be varying. So all electrons will have kinetic energy minus h cut square by 2m del square. So we have to add all the Z number of electrons kinetic energy. So that is why summation over J1 to Z minus h cut square by 2m del J square. And these electrons are having potential energy also, because there is Z number of protons inside the nucleus. So because of the protons, it will have a Coulomb potential energy. Positive charge and negative charge will be creating a Coulomb potential energy, and that will also be for each electron. It will be summation over. We have to do the summation over. So 1 by 4 pi epsilon 0 is a d squared by Rj. So each electron will have a potential energy. So we have to take the sum over. So we have the first part. Now the second part, half 1 by 4 pi epsilon 0 sigma over j not equal to k to z e squared by Rj minus Rk. What is that part? I will explain later. That is the interaction part, because of the exchange of the exchange energy between the electrons and protons. So if the J is equal to K, that means J is equal to J, isn't it? So that means the same particle will not have any exchange. There should be two different particles or electrons or protons should have an exchange energy. That is what the exchange energy creates. That is why we have put half there, because the total number of particles will be 2Z, and we have to take the half of it, because we are taking two particles there. So total will be double then. So we have to take the half. Half 1 by 4 pi epsilon 0 e square by Rj minus Rk, where j is not equal to k, and we have to do the sum over up to Z. So this is the interaction part between the particles. That is also interaction potential energy. Okay, now we have for helium, let us take, this is for any atom having atomic number Z. Equation 1 is for any atom, but now let us take for helium. It is we have to remove the summation. We need only two electrons and 2 protons. So let us take 2 electrons kinetic energy, and that is minus h cut square by 2m del 1 square and minus h cut square by 2m del 2 square. The first term in the bracket, 2 brackets there. And the next second term, 1 minus 1 by 4 pi epsilon 0 2 e square by r1 is for the first electron with the proton, and second electron, it is the second electron with the proton. Minus 1 by 4 pi epsilon 0 2 e squared by r2. R1 and r2 is the distance between the nucleus and the first electron, and nucleus and the second electron, R1 and r2. And there should be an interaction energy also between the particles, and that should be 1 by 4 pi epsilon 0 e square by r1 minus r2 between the electrons. Okay, now we have the total Hamiltonian there. Now next, what should we do now? We should equation number 2, we have the Hamiltonian. Now we are going to ignore the last term, the interaction term. We are going to ignore it because it will be very difficult to include that too for finding out the wave function of this solution of this equation, If we ignore the last term, we can use the Schrodinger equation with the solution as the product of two hydrogen wave functions. That is, we have here two electrons, so each electron should have a wave function, isn't it? So first electron have psi r1 and second electron have psi r2. So for hydrogen there was only one electron, so we need to take only the wave function of one electron. Here we need to take the product of the wave function of two electron. That will be the resultant wave function of the helium atom. So psi r1 r2, r1 is the position vector of the first electron and r2 is the position vector of the second electron with respect to the nucleus. So psi r1 r2 is equal to psi nlm. Nlm denotes the quantum numbers of the electron, first electron. Psi nlm r1 and psi n prime l prime m prime r2, and n prime l prime m prime are the quantum numbers of the second electron. So equation 3 is the solution of the helium atom Schrodinger equation. It is the helium atom's Schrodinger equation. Okay, we have assumed this solution, equation 3, as the solution of helium atom. And now which has this has only half the Bohr radius and 4 times the Bohr energies. We have already found out in hydrogen atom, we have already found out in your BSc classes that the energy of the electron, the first shell, second shell, all this you know. And hydrogen atom only we have studied. So here we are saying that the Bohr it has only the half of the Bohr radius. If you go into the equation of radius of the electron's orbit in hydrogen atom, you can see that when the atomic number increases, it will be decreasing. The Bohr radius will be decreasing. You can check it in the textbook. It is this part is referred from David J. Griffith, quantum mechanics from David J. Griffith. So you can see this in the book of that. Okay, now the energy, how will it be changing? It is changing 4 times the Bohr energy. That is, we have here 4 particles, 2 protons and 2 electrons. So the energy will be 4 times the particles. So 4 times the energy. En and En prime is the En 4 times En plus En prime. What is En there? En is the first electron's energy, which is minus 13.6 electron volt divided by n square, and this is same actually because the second electron also is in the same orbit, so En prime is also the same as En, so it will be 4 times the Bohr energy. Now equation 4 gives the energy and equation 3 gives the wave function of the helium atom. Now for ground state case, we say that the wave function will become psi 0 r1 r2. Instead of psi r1 r2, we say that psi 0 r1 r2. And what will be the value? N will be 1 and all other values will be 0, isn't it? So psi 100 r1 into psi 100 r2 is the ground state wave function of the helium atom. Equation 5 is the ground state wave function. Now let us write the ground state energy there. It should be 4 into what is that? 13.6 eV divided by n square. N is 1 there, and why it is 2 there? En plus En prime is there, isn't it? So 2 electrons are there. That is why 2 is multiplied there. So 4 times 2 into minus 13.6 eV by 1 square. And that is 8 into minus 13.6 electron volt. And that is equal to minus 109 electron volt. Now, here psi 0 is symmetric. You can see that psi 0 is psi 100 R1 into psi 100 R2. So it is symmetric. The spin state has to be anti-symmetric. As the spatial part of the wave function is symmetric, the spin part should be anti-symmetric. Otherwise there will not be you can say that in Pauli's exclusion principle, no two electrons should have same all quantum numbers. So at least one quantum number should be changing. Here N, L, M are all same here, isn't it? So only the spin should be changing. So here psi 0 is symmetric. The spin state has to be antisymmetric. Spin, if first electron has plus half, the second electron should have minus half. So the ground state of helium will be singlet state. That is singlet means two states, that is one plus half state and minus half state. The other one minus half state. And it is called singlet state with the spin oppositely aligned. Okay. Now it is experimental proof should be required. For helium atom, the energy is experimentally found. The ground state energy is experimentally found, and it is equal to minus 78 only, and minus 78.97 electron volt only, and that is in disagreement with the calculated minus 109 electron volt. Why is it? Because it is because we have ignored the third term here. See, 1 by 4 pi epsilon 0 e squared by modulus of R1 minus R2, that term, the interaction term we have removed. So that is the reason why we have the experimental result and the calculated result is in disagreement. So we know that we have ignored the electron repulsion term and the last term, that is the last term in equation 2, which is certainly not a small contribution. So that term should be giving a contribution. That is why we have a small difference from the calculated value of the energy. The wave function with a spatial part symmetric and spin part antisymmetric forms the parahelium state, while the wave function with antisymmetric spatial part and symmetric spin part forms the orthohelium state. That is, I have already said that the electron in helium, that is here, the ground state contains the 2 electrons, isn't it? So it gives the spatial part psi, which is symmetric, and the spin is antisymmetric. I said that, and that is called parahelium. And if you have the spatial part antisymmetric and spin part symmetric, that state we call it as orthohelium state. Sometimes this helium in the ground state can go up to the excited levels, isn't it? It can absorb energy from any other source, and electrons can jump into the excited levels. These excited levels can be orthohelium or parahelium. So ground state, we know that it is parahelium state, but it can go to excited state also when it absorbs energy. So we can say that it can go to orthohelium state also. The upper energy excited level can be orthohelium state. I will show that in a diagram later. Now the ground state, we know already that it is parahelium. The excited states can be both parahelium and orthohelium forms. As the symmetric spatial states brings the electron closer together. This you will learn in a part where which is not there in the syllabus, the exchange force part. I had sent it in your I will send it in your classroom, Google Classroom, those part also. That is not there in our syllabus, but you need to read it. Just read it and you will understand this part. As the symmetric spatial states brings the electron closer together. If you have two electrons which has symmetric spatial state, then what happens is that these electrons will come closer. And if you have anti-symmetric spatial states, these electron will not have smaller energy when they are close. They should move apart. They move farther away to get the lower energy, lower interaction energy. So if the symmetric spatial states brings the electron closer together, we expect a higher interaction energy in parahelium. And you can see it is the previous section in exchange forces, and this also experimentally confirmed. This is also experimentally confirmed. So as the when you have a symmetric spatial states, it brings electrons closer together. That makes the interaction energy higher. You can see it in the exchange force region. I have read it, I understood. If you don't understand it, please ask me. It is I will send it in your Google Classroom. All this part, exchange force part, it is in the Griffith's book. Okay, this is also experimentally confirmed. I will show that in the next figure. See this, the oneness level, which is parahelium, we don't need to worry about it. It is parahelium. It has symmetric spatial state, but we have 2s state in parahelium and orthohelium state. So see, 2s here 2s in parahelium is having higher energy than 2s in orthohelium. Similarly, 2p in parahelium is having higher energy than 2p in orthohelium. So 2p in parahelium means symmetric spatial part and antisymmetric spin part, and 2p in orthohelium means antisymmetric spatial part and symmetric spin part. So that is what we see in experimental energy findings. When they experimentally find the energy of these, you can see this. So 2p have both parahelium state and orthohelium state. We know that 2p, x, y and z are there, isn't it? So this is one of the value in parahelium, 2p, and in orthohelium also there is 2p, and here 3p also is there in parahelium, and in orthohelium also 3p and 3s. So you can see that in parahelium it is little higher energy. Because of the symmetric spatial part, the interaction energy increases. That is the reason. If you read the book, textbook, you will understand it more clearly. Okay.